here's what they do. There's no sound. Don't worry, we'll get to gravitation in a minute. Let's just have a look. So they start with this film of soap. Watch what happens. You can see the fringes, you know, you're going to get different coloured fringes due to the thickness of the. What's happening is that over time the film is draining to the bottom. Yeah? So the top of the film is getting thinner as it, and the bottom, so it's like wedge shape. It's really, really fascinating. It's just fascinating what happens. And the physics is not difficult. Watch the top of this film. Notice, can you see that green is reinforced regularly? Green, 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 green. This is because here the thickness is equal to 1 green wavelength, 2 green wavelengths, 3 green wavelengths, as it gets thicker, so you get these.
Others are becoming more.
Yeah, but look what happens at the top. The top's really interesting.
This is in real life view, right?
Yeah, this is filmed in Massachusetts.
Slow motion.
That's real time. This is real time. It's like 4 videos about 4 minutes. You see what's happening from the top? Isn't it fantastic? And that's not, the film hasn't burst here. There still is a film here. It's just that it's become completely transparent. It's not reflecting, for some reason, there's no light being reflected off this. All wavelengths are being cancelled. It's fascinating. And so as the film gets thinner and thinner and thinner from the top downwards, you get to this point where all wavelengths destructively interfere. None of them reflect. It is interesting, isn't it?
Maybe it's reflecting like infrared light.
I could expect that the explanation of why this path goes black and white is relatively simple to understand. If you remember with thin film, remember the constructive or destructive interference depends on, you've got the phase change due to the reflection of the upper surface together with that path difference due to the thickness of the film. Yeah? If the film becomes very, 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 very narrow, then the path difference due to the light travelling through the film becomes negligible, becomes insignificant. And that means all wavelengths will experience, all light of any wavelength, all of the wavelength lights experience that phase change on reflection. Yeah? If the thickness is very, very thin, then you don't have to worry about any additional path difference due to the thickness of the film. So all wavelengths just experience the same phase change when they're reflected. They are all destructively interfered. Does that make sense? Yes? You see, Jesus, that makes sense. So as the film gets thinner and thinner and thinner, you get to a point where it goes black. No wavelength light is reflected on. That happens apparently, according to MIT, at 10 nanometers. So when the film becomes 10 nanometers thick or less, then the path difference due to the path through the film becomes irrelevant, and all wavelengths just suffer that phase inversion on reflection, which means they all destructively interfere, and it goes black, which is what you see there. It's just fascinating. Yeah?
Before that happened, you could see as it was thinner, there was more diffraction.
Yes.
The colors were more resolved for white.
Exactly why.
And to get more resolved, then go to.
And if you look really, 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 really carefully, the first bright fringe you get here is blue. Now that makes sense. I'm saying that
Blue is.
think about this. The more you think about it, the more interesting it becomes.
So maybe it isn't the most useful stuff becomes.
I never said it is useless. It's absolutely useless. It's interesting. It's fascinating.
I found a use for it. Now you can measure it really small distances, by looking at the light which comes through.
You could, yeah, you could measure. Yes, exactly. You could work out the thickness of the film by looking at the light. Yeah. Why would you do that?
Yeah.
The point, the real application of this is very, as I said, there's a significant application of this. If the film is less than 10 nanometers thick, then all wavelengths destructively interfere and no light reflects off the film. And this, therefore, films which are transparent films less than 10 nanometers in thickness act as anti-reflective coatings. So if you take a glass sheet and you coat it with a film which is less than 10 nanometers thick, then all light will be destructively interfered. No light will reflect off it. Yeah?
So what they
So it's an anti-reflective coating. You know, sometimes when you picture frames, you have a picture, yeah? Mr. Folland. Like that. There, and it's behind a glass sheet. But sometimes it's on your wall. Sometimes you can't see the picture because the glass reflects. When you look at the picture, all you see is the window or your Filipino maid doing something in the kitchen, yeah? Because light reflects off the glass and you just see the reflection in the glass and not the picture behind it, yes? Solution? Coat the glass with a thin transparent film, less than 10 nanometers in thickness. What will that do? It will effectively eliminate light reflecting off it, yeah? It's an anti-reflective coating.
Will light still reflect from it, but just won't like
Light still reflects from it, but all wavelengths of light will be destructively interfering after they reflect off it, and therefore effectively there is no reflection.
Wouldn't that be so useful for TVs? You know how there's plasma TVs that so much light reflects off.
Yeah, anti-reflective coating is a major application of this, and then, you know, in optical instruments, cameras, telescope lenses, television screens,
Couldn't this
pictures.
be potential IA? Because that has a real life application.
It is.
As an experimental procedure.
Yeah, but I'm not sure how you could possibly. Yeah, possibly. How would you make it into a quantitative investigation is the question.
How long does it take for?
Yeah, you can look at the rate at which the
If
film
they
is.
perfectly interfere, won't that make sense?
Okay, I don't know.
Be surprised if they perfectly interfere with each other, won't that make it standing wave and then like you can see it every like once every nanometer or something like that?
Yeah, I mean, you could what you could do is you could start investigating the distance between those fringes. Yeah, because you know they get closer at the bottom, and that will tell you something about the gradient of it. You could do some interesting.
Yeah, I mean, they're going dark, like the waves interfere with each other, but won't that make a standing wave if the wave is reflected and then it's superposed on another one? So shouldn't it be like, shouldn't you get
Something reflective.
because you said that the way that the film is so thin that the phase difference between the
I suppose you're talking about in between your eye and the film, that incoming wave and that one coming out. They are going to interfere, but you don't generally get standing waves of light. It's a bit, what do you do?
well, that's, yeah,
I get what you're saying, but
it just cancels out completely all the time.
Yes,
Shouldn't it like if this one's going, you know, like they will, you know.
they will always cancel out. You won't get a standing wave, you'll just get nothing. Ever. At any point. I think. Well, anyway, look, that was by the by. Let's get back to what we're doing, which is Kepler's third. Kepler's third.
Yeah, maybe we'll
Now, at the end of the last lesson, I asked you to take some data and try and analyze it using data of periods, of orbits, orbital periods, and orbital radii of the planets in the solar system, and to try and do a log-log analysis to work out what the relationship is between the period, of orbital period of the planet and its distance from the sun. And this is Kepler's third law. We did deduce that experimentally from our experimental data with astonishing precision. And that astonishing precision, as I said at the end of our session, is 5 Newton. What do we have? T squared is equal to K R cubed. And that's Kepler's third law. Right. Interestingly enough, there was one planet in the solar system which didn't follow this law precisely. As you saw from your data, it's a 1 r squared is 1. Yeah? It's phenomenal. But there is, the more they examined and made accurate measurements of the orbital periods of the planets around the sun, they realized that there was one planet which didn't quite follow this law. It was out by like 0.0001%, and that was Mercury. Okay? The orbit of Mercury, for some reason, just was sort of, you know, a very small disagreement with Kepler's Mercury. But it was enough to get people worried. I mean, it was only like a 100th of a percentage difference, but the measurements were so precise that they were sure there was a difference. In other words, it comes to the scientific method. In science, theories are falsified. You can never prove something to be true. All you can ever do in science is prove it not to be true. You can prove something not to be true, but you can never prove it to be true. So we're on a bit of a loser really in science. So this problem with the orbit of Mercury sort of falsified Kepler's third law, and therefore used these ideas of gravity. And that's what inspired Einstein to come up with his general theory of relativity, which deals with gravitational fields in a very different and revolutionary new way. And the great triumph of Einstein's theories was Einstein's interpretation of gravity accurately predicted the path of Mercury. Okay? So it's of historical interest. Yeah? Okay, right, let's get to business. What does this mean? The main application of this is you can take any planet in the solar system, and if you take its orbital period and square it, and divide the square of its orbital period by the cube of its distance from the centre of the sun, you're going to get a constant. Okay? So it doesn't matter if you take T1 squared over, let's say if you look at Mars, you take the orbital period of Mars, square it, and divide it by Mars's orbital radius. That must give you the same answer as if you were to take the orbital period of the Earth, square it, and divide it by the orbital radius of the Earth cubed. And so the ratio T squared to R cubed is always going to be the same for any planet in a particular given solar system. Yeah? Or for satellites moving around the Earth. There's something like 6,000 satellites up there orbiting us at any given time. Yeah? For every one of those satellites, if you take the period of the satellite's orbit around the Earth, square it, divide it by the distance of that satellite from the centre of the Earth, cubed, you're going to get the same answer. Yeah? So that ratio is the same for every single one of those thousands of satellites orbiting the Earth, and that ratio is the same for every planet orbiting the Sun in any solar system anywhere in the universe.
What the moon, because its orbital radius from the sun is changing because it gets closer at one point, I guess.
Yeah, the Sun's gravitational field messes things. If you're looking up the moons, or if you took if you worked out this ratio for the moon, which is orbiting the Earth, and compared it to this ratio of a satellite, which is orbiting in the Earth, you should get the same answer. They will differ slightly because the Earth is not the only thing that is exerting a gravitational force on the moon and the satellite, also the sun is. Okay, so that there might be slight differences, but essentially they'll be the same. So that's the great sort of problem-solving benefit of this law. And it's really your key to unlock most multiple-choice style problems, and even paper 2 problems on Kepler's law. This is the format of the relationship which is most useful to recall. Of course, it's not in the data bucket, yeah? But that is the format of the formula which is most useful from a problem-solving point of view. Yeah? And we'll look at some problems in a moment. Yeah?
So the mass of the planet has no effect on its
No.
period.
Interestingly enough, you might expect it to. It doesn't. But then again, mass often cancels out when you're dealing with gravity. Yes? All objects accelerate at the same rate, regardless of their mass. It comes as no surprise when the mass of an object doesn't appear in a formula or relationship which has got something to do with gravitational fields. It shouldn't be a surprise. Yeah? Because masses tend to cancel out. Right, okay, well what I'd like you to do is to prove this. And I'm not going to prove it for you, I'm going to give you the opportunity to impress me, to earn some respect from us. Okay? By trying to prove this, and I'm going to give you a challenge. I'm going to ask you for, I want you to develop, tell me what k is equal to, okay? I want you to develop this, I want you to prove this relationship essentially, and tell me what k is, and you know what this constant is. I'm going to give you a clue how to prove it, yeah? If this is the sun, and this is the Earth, or any of the planets, yeah? We're obviously dealing with circular motion. Do you agree? Yeah? Now, we know that the velocity, let's call that the mass of Earth, me, yeah? the mass of the sun, ms. All right, all of this. And the Earth, we can say, is travelling at a velocity v. That distance is little r. Yes? What we know, because it's circular motion, that the force acting on this planet, on the Earth, to keep it orbiting around the sun must be equal in magnitude to the mass of the Earth, e squared over r. Do you agree? Circular motion. If something is moving in the circular path, then the net force acting on it must act towards the centre and be equal in magnitude to the mass of the body multiplied by the square of its velocity divided by the distance. Yeah? Okay, but the great thing about this example of circular motion is it's so goddamn simple, because there is only one force which is centre acting, and that is gravity. You know, it's not, we have many more complicated circular motion situations where you might have two, like a pendulum swinging through its lowest point. So there are two forces which are centre acting, you know, weight and tension. You remember those questions. And it's the sum of those forces which is mv squared over r. This is a very, very simple situation. There is only one centre acting force, g squared, and it's gravity. So that centre acting force, we know the centre acting force in this case is gravity, and we know that it's the gravitational force acting on the Earth. Yes? That statement there will take you eventually to this. You've got to get from here to here. Let me put what we know already. We know that the gravitational field strength at any point away from the sun is equal to gm over r squared. And we know that the gravitational force acting on the body placed in the gravitational field is the mass of the body multiplied by the strength of the field. Yeah, at that point. Then, and this, you should be able to get to that. 5 minutes, off you go. See if you can do it. It's not difficult. But notice, I'm going to give you a chance to do it. I'm going to wait until I can see the frustration in your eyes. I have to say, I'm expecting you all to fail this task. Yeah? Claudia might have succeeded, but she's not here. But she is. Alright.
Oh, you're recording.
It's being video.
Oh. You guys just hate Claudia.
Work together, work in pairs. It's not a solo activity. You need to get your heads together. See if you can. You've got to get from here to here. Okay, you've got to think about what is the gravitational force acting, an expression for the gravitational force acting on the Earth. That should be relatively easy. That expression in there. Kepler's laws actually in the data. I think you might have to turn on. Good.
Okay.
At least you've realised that period appears in the final thing that you've got to show, but it doesn't appear in the so somehow you've got to introduce period.
Which is why you use it.
No.
2 pi r.
But the period, the time taken for something to go around the orbit once is 2 pi r, the distance travelled, divided by a speed 2 pi r over v. So if you can get, and v appears here, so you can make a substitution. Yeah?
Yeah.
That v can be substituted. Be careful with the masses. Mass of the Earth, mass of the Sun. Be very careful not to get the masses confused. Yeah? You've got the mass of the body, the Earth, and then you've got the mass of the Sun, things creating the field.
Så Palle,
Anyone get something?
Anyone get any extra say? Don't walk away and sleep. That must be gravitation. Gravitation. A mass of the object multiplies by the mass of the object. And we can cancel. Well done. Yes, the quiz you has got there, which is encouraging, which is I'll give you a further clue. The other result you're going to need to use is this one here. That the time taken to go in orbit is the distance divided by the speed. Yeah? Time is distance divided by speed, essentially. Yeah? So that will allow you to introduce period into the maths. If you actually look at that, so NB squared over R is equal to the gravitational force acting on the Earth. Right, gravitational force acting on the Earth will be the mass of the Earth, NB, multiplied by the strength of the gravitational field of that, which will be G as over R squared, where N is the mass of the Sun. Yeah. I think that's what we've done there. You're going to give very good. Anyone? It's just a little bit of it's good old-fashioned physics.
Yeah.
Well done.
It's
It's the mass of the Earth. It should cancel out.
So it's really the
Is that not
Is that- I think I know what you mean.
Yeah.
Oh, you have to.
You've got to be careful on the mass.
Yeah.
Yeah, I think
Because you know, force, the gravity is M times G. Yeah? G is that. Because of
Okay, I'll show you on the board. I think we'll let's go through this. Let's start at the very beginning. For the Earth, okay, for the Earth. Let's consider for the Earth. And by the way, interesting grammar. Let me be an English teacher for a moment. If you say for the Earth, little e, or you can say for Earth. You don't need the when you're referring to Earth. Yeah? But if you drop the then it has to be a capital E.
okay.
For Earth, right. The gravitational force acting on the Earth must be equal in magnitude to the mass of the Earth, v squared over r circular motion. Do you agree? Yes? What's the gravitational force acting on the Earth? It's the mass of the Earth multiplied by the strength of the Sun's gravitational field at that point. The strength of the gravitational field that's acting on it, G. So that's the gravitational field of the Sun. Okay, is equal to mv over v squared over r. Now the strength of the Sun's gravitational field at that point, gravitational field strengths drop off, they depend on the mass of the body, which creates the field, and the distance. So the strength of the Sun's gravitational field at this distance from it will be g times the mass of the Sun, ms, divided by r squared. Do you agree? Yeah. And that must be equal to mv squared over r. Masses of the Earth cancel out. Correct? Now this r also cancels out with
One of the others.
one of those, which gives me g ms over r equals v squared. Correct? Now I can make a substitution from here, because v is equal to 2 pi r divided by the period. Yes? Put that in there, we get g ms over r is equal to 2 2s are 4, pi times pi is pi squared, r times r is r squared, all over t times t to t squared. Yes? Now, simple rearranging, t squared is going to be equal to 4 pi squared r cubed divided by g m, where m is the mass of the star or body which the things are orbiting. Yeah? So the constant in Kepler's third law is pi squared over gm, where m is the mass of the astronomical body which the things, the satellites are orbiting. Okay?
There's also a different way of doing it. There's a different way of doing it.
There are many different ways of doing it. Yeah.
It's like circular motion. It's on the beginning, instead of mev squared over r, you could convert it to me 2 pi over t squared r.
Yes. You just make the substitution right at the beginning. Yeah, you just substitute earlier. Yeah.
Squared.
I mean, t squared is just saying you could have made this substitution right at the beginning. You could have said right at the beginning, well, let v squared equal this squared. Yeah. So you could have made that substitution right at the beginning, and then the rest of it is just rearranging and cancelling. Right. So maybe that's a better way of doing it. Okay. Yeah, it's just, that's how we can get to the Kepler's third law theoretically. Yesterday we got there from an observational, empirical way, with observational data. Here we can actually use our ideas of circular motion and Newton's ideas of gravity, Newton's gravitational laws, to get there theoretically. This is what Newton did. Yeah?
Even the orbit is an ellipse. I think this works so well.
It still works from ellipse, okay? And Newton's equations, his laws of gravity, equally apply to elliptical orbits. The answer to that, to explain why that is the case, involves integration. But you can find out online. It's within your abilities. Yeah?
Mom, how come, I'm lost of the v squared. You change it into period, right?
I've just made a substitution here. Yeah?
V equals, isn't that the period though?
Yeah, that's the period. So the speed at which the planet is moving is the distance it travels once around divided by the time it takes to travel once around. This is just speed is distance divided by time applied to one orbit of the planet. So the time becomes the period and the distance becomes 2 pi r. So you can always substitute for speed in any circular motion problem. You can always substitute the speed of the object, the body, with 2 pi r over t if you want to introduce a period into your equations. Yeah? Okay. So, yeah, relatively straightforward mathematical proof. Right. So, I've got some past paper questions on Kepler's third law, which I picked up, and they are over here. Something like this, required to solve this one. If we've got a little bit of time at the end of the lesson, a little bit of free time, I'll set up an experiment for the attendance. Next week, by the way, remember, is IA all the way. So really, guys, if you haven't already finalised an IA question, you need to give a long, hard think about that over the weekend, so that when you come in with the first lesson next week, you've got a possible research question. I would really like it if the majority of you could, get your research, your hypothesis, and your data collected, so you can go away over the holidays and basically work on the first draft. It would be hugely advantageous for you guys.
For the class, then you want the evaluation?
No. We'll leave it at that. Because I've got to sit down and work out how I want the evaluation structured, so that it fits well into this new assessment practice. Yes. Claudia, it's in exercise, is in the Dropbox. Perfect, there you go.
And it could give it potential to move my lucky ideas.
When are you going to get your data? When's our first lesson?
Not sure. We'll do it on Tuesday. Tuesday.
I have free periods. You have free periods. No free periods at all next week.
It was the only free period was last lesson Tuesday, so then
What about Saturday?
Oh, I know this one. Yeah.
you can change the future. I realized something. I started at 19 and moved down each
Exactly.
Once you change what each time you increase by 1,
That coefficient can't have a value greater
No,
than
there's no
That's the way it is. So the rank coefficient, by definition, is a value between 0 and 1, so I'm not quite sure. Simulation 1 to simulate.
Yeah,
That's it. Does it already?
Your map side.
Or three.
But it's not that, not I was so surprised when I found it. I just kept like, you can move this up, you can move that.
On the map side, you could develop develop laws of motion in regard, and then you can actually use this simulation to get data.
And then I could use these.
Very nice. They really like the use of simulation. So you could do that. Would be a possibility. You could test your hypothesis, your mathematical equations using a simulation. Yeah. Yes, I think it's not. It's a good idea. Yeah.
She's saying there's not enough math.
Oh, there's more. Trust me, there's a huge amount of maths.
Like it's not a high level math.
Oh, there is. It's
What is it? It's
massively because it involves differential equations.
That's fundamental.
Differential equations is not standard level. Differential equations, d2x and dt squared plus a solve this equation. I mean, this is what when I say differential equation, I mean something like this: d2s a d2s dt squared plus b ds dt plus c.
So it's a quadratic equation.
All I want to know what is s. See, can you get that? Can you extract it? Can you find a function of s in terms of t which satisfies that condition? Tell me that.
What did he say?
Quadratic differentiation.
That's the second order linear
So is
differential equation.
this it by any chance?
What's it just be like?
Yeah, this is finding it's showing how you come up with it.
Yeah.
Which is what I have. So far, it's not much what I did. It's very modern. But I basically wrote, this was what is the optimal angle for taking the song about because that's something personally really I said as a young child, this song is BS. And then I came here, so if you
Hang on. Hang on.
Yeah.
Yeah, just checking for bottles of water.
I talked about how you can conservation calculus and projectile motion. I said calculus effective friction and other forces extremely strong and complex calculations. Said the assumption objects should follow the parabolic trajectory, which is the path followed the force on gravity on that side. I said I was supposed to be symmetric, and I said that I was showing the vector motion traveling two dimensions, the stress on x and the x and y dimension, showing the overall vector in two components only. The estimate's pretty much right about it. Yeah. It's quite a complicated topic. This is what I was going to start off with.
I think she wants to move in energy.
That's right. If you're really likes mixed field physics, they're going to do very complex simulations.
And like, you know, have an intro to that.
Things have to be.
And the other thing.
They encourage the use of simulations for personal investigations. They say personal investigation based on simulations. So you can get data from the simulation. But an extended essay, I would much prefer to see an attempt made to get the ring out of the data.
Where's the file?
You want it?
So there are many recommendations for technical motion force. This is without
air resistance.
then I have to derive it with
With air resistance, that's the challenging part.
Yeah. And then basic optimization. After finding out the maximum the angle which
Yes,
does
you need to come up with a function of range as a function of angle, so initial velocity, and then you need to differentiate that to find the optimum value. That function of range with air is only quite a complicated function.
I feel like, you know how they have the mix between math and science?
How much technology are you allowed to use in your maths? The easiest way to solve projectile motion with is the use of technology, is to use Excel, as I explained previously. You sort of go like add 1/10 second, add 1/10 second, add
Number 2 or number 3? I guess.
What?
I just matter something
The other one you can do, which is relatively straightforward, which is higher levels as well, is harmonic motion. It's a very good example of what is managed as a second differential equation to determine the relationship of mathematically that formula is this. I can give you very straightforward. Yeah?
Is it?
Yeah, that's just.
Potential. Is that a lot of math?
Oh, it's good maths. It's Julia's complex numbers. I mean, there's no doubt on that. The content is commensurate, and you can actually get lab data to prove it. I mean, one thing is to try and prove it as data to verify. It's nice if you can. Or you could use a simulation to do something. You got if something is swinging, oscillating harmonically, the amplitude decays. Do you agree?
Yes, yeah.
And that decay is exponential. You can prove that mathematically.
That's like the said SS was going to physics.
Yeah, that's an easy thing to prove mathematically. You can make it relevant. You can look at any example of a simple harmonic oscillator. Again, it's just basically maths. I mean, there's so many options. So as long as the maths is there, the overlap. They don't seem to be so worried about the overlap between maths and physics. I asked Screw about that yesterday.
Screw-ish.
Well, Danny's doing one on wheelchairs. Are you doing one on?
Yeah,
Yeah,
she told them.
essentially, to me, that's physics as much as
Yes,
it's maths.
she told me there's not enough math in yours.
No, there's maybe not high level maths.
There's not enough higher
There's
level.
no
I
high
also
level.
learned that I'm not doing it. Like, I'm not gonna get more than 2 for the math.
You only get marked down on which criteria.
What about the use of math?
Use of maths.
If you map by
And if you think about it, if it's not commensurate with HL, then the maximum you can score is 3.
Just 4.
Two, isn't it?
No,
No, you can actually get 4 if.
Yeah, if
If
it's
it's-
high level.
Huh? If it's not that higher level.
Yeah.
No, if it's not that higher level, but it does like touch on subjects that are part of the higher level, but also part of standard level, then you can get actually 4.
4.
Yeah.
Yeah.
And like what I saw,
think you'd end up with 3.
Yeah.
First.
I saw this
And
thing.
then, even if it was a high level topic, you're never going to end up with 6. So if you chose a high level, you redid it as a high level topic, you're going to get realistically 5 out of 6. At the moment, you're going to get 3 or 4 out of 6. So you're talking about 1 or 2 marks out of 10.
And the communication is good.
And the advantage of doing a relatively simpler mathematical concept is it's easy. You understand it better. It's easier to present, understand, communicate,
And you can maybe
yeah, engage,
like 4 marks
people
here.
engage, actually understand. So you actually, your chances of increasing your score in the other criteria go up. So if you weigh the pros and the cons, and I was discussing this in this room just an hour ago, it's probably in your situation, it's worth just saying, well, you've got take the hit 1 or 2 marks.
Or give a slight, like, just add a bit more. He could easily add a bit more. Plot in a graph somewhere. Use optimization. But what about
doing some physics? How many of you? I just keep saying get on with physics. I'm not keep interrupting you again. Actually, know what you're doing with your personal investigation in physics. Usually does. You like this.
Didn't I?
Terminal velocity.
Terminal velocity. Yeah.
Don't you? One, do you think that?
It was research.
Six air parachutes.
Yeah.
I think I did, do you think it's a good idea though,
I think parachutes. I'm hesitant about that. I've done parachutes so many times, and it's really tricky. I think time consuming to get your data. If you want to do terminal velocity, you might be better off just trying to simplify it a little bit.
There's nothing like that. Can't do the microwave one, because the microwave is unless you can fix the microwave.
Yeah, you can do parachutes of different size, try and work out, literally use video analysis. Calculate.
This is the boss.
I probably don't know the exact relationship, but you might be. I would propose this power relationship of this form.
Which one? This is from last time. If you can't find anything, just go look on the website.
Did you talk to them? Did you ask them if doing something off the bring your website is okay?
No, I haven't actually, but it is okay. I mean, it's a process where and there are straightforward terminal velocity experiments you can do with linear motions, dropping trays and weighting the trays by different amounts to see how the terminal velocity depends on the mass of the object. Well, the other thing you could consider is I'm just thinking too, is the thing of parachutes going to be very tight to get rid of the data. These are balls which are basically looking at balls which are same diameter, different masses. So let's see. In theory, they have different terminal velocities. So you might want to you could use that, drop them through a column void around the air. That's a possibility. Terminal velocity is a good area.
Is it easy? A bit. Straightforward. Good.
So when it says state Kepler's third law, we just say T is proportional to T squared proportional to R cubed.
Yes. Period square of a period of an orbital is proportional to.
Yes, it's 5G.
Says T squared.
Well, it's easy.
Is that useful?
I don't know. Mas tem que ser algo que eles vão tem que ser algo que eles vão tudo.
Super set.
É.
You know why?
Most of these questions are relatively straightforward, aren't they? Kepler's law, the square of the orbital period of a satellite.
Just put T squared is proportional to R cubed.
Yeah, that's okay, but you're going to have to explain what T is.
Period.
And what they apply to, i.e. orbiting bodies. For an orbiting satellite, and the word satellite in physics, satellite is anything that orbits anything due to gravity. So the Earth is a satellite of the Sun, the Moon is a satellite of the Earth. So generally orbiting, things which are orbiting around an astronomical body, that is the Earth, the Sun. Kepler's third law, as you said. The square of the orbital period of satellites is proportional to the cube of the orbital mass. Or you could say the ratio of the square of the orbital period to the cube of the orbital radius for any given satellite is constant.
Yusuf has about it. You know. Yusuf, work on it.
There's a graph of population of some rats in the US. They try to put it in an X squared line with the word drop. Literally the word drop.
Is it fine?
It is garbage.
Bro, this is
So fun.
Why?
I don't know, bro.
What's the word? Is it like really long or what? Is long or what?
Multiple choice answers, boys and girls, and Claudia. Number one, numero uno.
B.
Correct. B. Number two.
B. A.
G squared has got B.
G squared is 1.
Anyone different? Who agrees with B?
I go B.
Because it says for the period of the square of the cube.
Which of the following is the correct expression for the period of the second planet in its orbit about to start? So you know,
Which one are you? 2 or 1?
question number two.
Oh, I got 8.
Because we know square root.
The period has got to be a square. It's got to be a square root. It has to be. It's got to be either B or it's B, isn't it?
1.
Because you can get an expression t squared.
You do?
Yeah.
T1 squared over R1 cubed, T2 squared. Yeah? Now rearrange to make one of the T's the subject. Let me show you.
Oh, and then square.
You've got to square root it.
Yeah.
You can rearrange to get T1 squared is equal to blah blah blah. Then you've got to square root it. So the square root comes in, which the answer is B. Isn't it? Yeah? Yes. Question number 3. A. Question number 4.
C.
C. Good. Well done. Question number 5.
B.
B. Question number 6.
T squared proportional to R cubed, where T is the
Oh.
period, R is the radius, and then you apply the square
Yeah.
satellites.
Okay. Name the force that provides centripetal force in 6B. Part 1 is gravity. state of the satellite, the orbital speed in terms of T and R,
V is
V is equal to 2 pi r at T. I think the rest of the questions are relatively straightforward.
Say the expression for gravitation for strength G.
So anyway, 10 more minutes on those. Yeah, that I eventually want to populate. Anyone who has anything to say yeah, that's exactly yeah, that'd be much appreciated. The idea, that was the idea of eventually. Right, guys, I'm going to stop you there because we need to do one more thing before we finish this work on fields and force, gravitational fields and forces. So I think that those questions are, go away. They're all past paper questions, the answers are there in the folder. Before I just do this last bit about Newton's laws of gravitation, in case I forget, Mohammed just mentioned that there is a folder in the Dropbox called SAT Physics. The idea why I created that folder was that if you have any PDF or Word documents which you use as sources for SAT Physics, the idea was that you can upload them into that folder and therefore they were available for everyone. So sort of shared resource file. And the hope was that over the course of years, that will become populated with resources which students have found useful and added. So it's a sort of common resource file. I'll add a few resources. You've promised to, you've got some SAT resources, you've got some. So if you could do that, it would be really appreciated. I'm sure future generations of students would appreciate it, not only for yourselves, but for the future. Because, secondly, as you know, next week is working on personal investigations. For those of you who don't have any investigations worked out yet, what I've done is under the lab work and internal assessments folder in the Dropbox, I have uploaded, thanks to Mercusi, this document, 300 Ideas for Physics Investigations, 300 ideas. A lot of them are pretty extended, maybe more suitable for extended essays, but still, lots of really nice ideas. Do any of those grab you? Read through them. Maybe something will interest you. And bring it to me in our next lesson and we'll discuss it. I've added this one here, another one, more ideas for physics investigations. That's from Nuffield Science in the UK and has some really nice investigations that you could do. And eventually I've got like 20 or 30 of my own, so I'll probably add a third document which I'll call even more ideas for physics. Yeah? So as it stands, there's probably around 400 possible physics investigations there, so I really don't see how anyone can not have a suitable idea. It's just going to be a matter of picking the one which matters. Again, I would encourage you to consider doing non-relationships or type 2 investigations where you're determining a constant. These are, can you come up with an interesting and original way of finding a value for G, or the speed of sound, or the refractive index of water? Liquids are very challenging things to work out. There are lots of possibilities, and the advantage of doing an investigation which is finding the value of known constants rather than investigating a relationship is that the evaluation is very, very straightforward. It's an easy thing to evaluate. You don't have to struggle with it. You've got your answer with an uncertainty, you compare it to the textbook value, straightforward, accuracy, precision. Why is it different? What can I conclude about my experimental method? It's a very easy evaluation and conclusion to write. So I would encourage you to consider, that type of investigation as well.
What type would it be if you're doing, like you're trying to make the data collection better, like the one that where you start off at like you start off at like 10 and then you get up to like 30, determining the specific capacity.
Well, that would be an investigation. You say that, okay, what is the specific capacity of water, and your objective in that investigation would be to develop a method. You would start by saying, we did this in class, I was unsatisfied by the values we got, far too many uncertainties. My personal investigation, I wanted to set myself the challenge of improving, developing that method, so that I get a better, more accurate answer. Easy to introduce, easy to show relevance, easy to conclude, easy.
What about the research question one? What is the
Research question is to what extent can
it's not how does this depend on this?
no, to what extent can an accurate value of specific class of water be determined using standard high school apparatus or something like that? That would be the research question and your aim. I don't think you actually have to have a research question. You have to have an aim or an objective. The aim or, if you look at some of those exemplars, they don't state a research question. They state an aim. My aim is to investigate this. Anyway, let's move on. Well, I've got to finish this business for 15 minutes left. G-square?
I just wanted to ask, is gravity like act on sound waves as well?
Sorry?
Is gravity act on sound waves as well?
No, not effectively.
Where does that come by?
Sound, the speed of sound as a variable, for example, is affected mainly by pressure, affects it, and temperature. Yeah. Again, a very interesting challenge to try and find out try and detect in the laboratory that variation, the speed of sound, and for example, temperature. How on earth would you do it? It's a challenging thing. But another challenge, how would you determine the speed of sound in water? That's challenging. That's not a straightforward thing. And it would be a suitable research question. What is the speed of sound in water? In distilled water also. Actually, if you think about it, try to. Yeah, well, exactly. It's an interesting, challenging thing. You go online and you say measuring the speed, I'm sure you'll find some ideas out there online about how it can be done. Right, okay, let's get back to this final thing. Newton's law of gravitation. I've left this to the end, whereas most physics teachers would probably have done it straight away. Start with this. I have left Newton's law of gravitation to the end. What is it? Newton's law of gravitation. Anything? What is it? Probably one of the most famous laws in physics. And what it does is it relates, or it refers to, it describes the mutual forces of gravitational attraction between two objects. So it is a law which attempts to describe the relationship between the mutual forces of attraction which two objects exert on each other. Right? So if we have a big planet and a small planet, could be the Earth and the Moon. Yeah? The Earth, planet B, will attract planet A, and A will attract B. They might just be a football floating in deep space and a ping pong ball or an apple. Yeah, it's just things floating. They will attract each other. Both of them are massive objects. They both have mass. They both have gravitational fields. The football will attract the tennis ball, and the tennis ball will attract has its own gravitational field, which will exert the gravitational force on the football. So if we limit ourselves to football and tennis ball, you release them in deep space, eventually they will come together because they mutually attract. They each have their own gravitational fields and they each exert a gravitational force on the other. Yes? So Newton's universal law of gravitation basically attempts to describe that relationship between those two mutual forces. Now, here is my initial question. This arrow forces in there. Red. B exerts a force of attraction on A. So I'll represent that with a red arrow. Does that make sense? And that length represents the force of attraction, gravitational force of attraction of B on A. Now I want to draw a similar arrow to represent the gravitational force of attraction that A exerts on B. I want you to consider the length of that arrow. Given that they have distinctly different masses, this is a football and this is a tennis ball.
Same.
They must be the same length. Good, I'm glad you said that. Now, can anyone come up with a reason why? Because the students are very tempted. I mean, just think about the nuts, the stupidity of what you're actually saying. You know, I challenge your answer. It's true, it's the correct answer. They are the same. But the more you think about it, that's a really, really outrageous thing. You're saying, if I hold an apple here, yeah, apple, that the Earth pulls on the apple, yeah, with exactly the same amount of force that small little apple pulls on the Earth. You're saying that they are equal, that the force that the apple attracts on the Earth, pulls on the Earth, is the same as the force the Earth pulls on the apple, even though one is obviously much bigger than the other.
That's the
Really?
That's the answer.
Really?
That there is
You know, it is an outstanding statement. The Kuzi.
It's because basically, although the forces are the same, the force acting on such a big object with such a heavy mass is actually not doing any work compared to the force that, because it's basically due to the relative difference between mass. Although the forces are the same, the force acting on a smaller mass is going to have a greater effect than the force acting on such a large mass. Therefore, the object.
Well, that explains why the apple moves to the Earth. The Earth doesn't. When you release them, the apple moves to the Earth, and the Earth doesn't move to the apple. Yes, I agree. The reason when you release them, they both attract each other. When you release them, you see the apple go to the Earth. Why? Well, the forces of attraction between them are equal. Yeah, you're right. The Earth is so massive that force has no effect on the Earth. The Earth doesn't move up. That force acting on the smaller apple means that the apple is the one that moves down rather than the Earth moving up. So yes, that explains why the Earth falls to the apple falls to the Earth rather than the Earth rising to the apple, for sure. But it doesn't explain why the forces are equal and opposite. Why a small apple can exert the same gravitational pull on a massive thing like the Earth, as a massive object like the Earth with a massively strong gravitational field exerts on the apple. The apple's gravitational field is very weak, and the Earth's gravitational field is hugely strong, millions of times greater, yet they exert the same amount of force on each other. Isn't that unusual?
Every reaction is equal and opposite.
You're not explaining
Every reaction is
Can I go out? On board?
Come back.
Oh, you did.
No,
that's
stay here.
the
Okay, so it really needs a diagram.
No, I don't need the diagram.
Go.
The force is mg, right?
Yep.
So that means that
The force acting on the body depends on two things.
On
The
its-
mass of
on
the
its
body
mass
and
and
the
the
gravitational
yeah.
strength of the field is
yeah. So even though the apple's gravitational field is so
weak.
weak, the Earth is so massive that it's the same. It just it compensates. They compensate for each other.
That is the answer, and I'll explain that to everyone in a moment. Yes. Basically, the apple, yeah, is in a very strong gravity. The force acting on the apple depends on is m times g. It depends on the mass of the apple and the strength of the field it's placed in. Yeah? Well, the apple has a very small mass, but it's in a very strong field. Yeah? Now, the force acting on the Earth depends on the mass of the Earth and the strength of the field it's in. The Earth is in a very, very small, the strength of the apple is in a very small gravitational field, yeah? But has a very massive mass. Do you see? The force acts, gravitational force is the mass of the object multiplied by the strength of the field it's placed in. Two factors, yeah? The apple has a small mass, but it's in a strong field. The Earth has a large mass, but it's in a much weaker field due to the apple, yes? So they cancel each other out perfectly, and the forces are the same. Good. Marcuse also argued brilliantly, which it was a brilliant argument, you can also explain why they must be equal and opposite from momentum. Because if I have that football and that apple in deep space and I release them, when I'm holding them there in deep space, what's the momentum of the system? Zero. If I release them, they're going to start gravitationally attracted towards each other. Do you agree? Okay? But at any point after that, the total momentum of the system must still be zero. Alright? Well, that means they must be both gaining momentum or losing momentum. They're changing, their momentum must be changing at the same rate. Do you agree? And for the rate of change of momentum is equal to the force. And therefore, since they must be gaining momentum at equal and opposite rates, the forces acting on them must be equal and opposite. Yes? So that's how Newton argued it, momentum. In fact, that was Newton's great insight. He used momentum to realise that all objects must have gravitational fields, not just big ones like the Earth. Genius. Newton was a genius. We can prove it mathematically. Okay, so let me show you how it's done mathematically. Yeah?
Who was the crazy one? Who was up to?
Oh, they're all crazy. Newton was crazy.
Was it Newton or was it
Newton.
This one, this force acting on A. Guys? Shh. Let me finish this off quickly. The force acting on A is going to be equal to the mass of A multiplied by the field strength of B. Do you agree? Yeah, let's call the separation R. Yeah? So that this force is going to be the mass of the object multiplied by the strength of B's field, which is G mB over R squared. R's the separation. Do you agree? Yeah? This force, the force acting on B is going to be the mass of B multiplied by the strength of the field it's based in, which is G, the mass of A over R squared. And these are the same. You see, they are the same. And basically, the mutual force of attraction is G MA MB over R squared. And that is Newton's law of gravitation. Yeah? When the gravitational force of attraction between two massive objects is equal to the product, or proportional to the product of their masses, and inversely proportional to the square of their center-to-center distances. Yeah? Okay, that's known as Newton's law of gravitation.
You don't take it as a point process, yeah? You take it as...
You do, because this distance r is from the center of one to the center. Yeah? Center to center. We deal with them as points. Does that make sense?
Yes.
Yeah, my diagrams here will attempt to explain that. Small mass in a strong gravitational field. Yeah? Big mass in a weak gravitational field. They both experience the same force. Yeah? Equal in magnitude or proportional to the product of their masses and the inverse proportional square of the distance. Classic question. What if I were to increase the mass of this one? Both forces would increase. Yeah? Changing the mass of either of the objects will affect the forces acting on both of them. Must do. Yeah? Yes? If I increase the mass or change the mass of either of those two objects, both forces will be affected in exactly the same way because the mutual force of attraction depends on the product of both of their masses. Clear? I think so. Sounds like you understand that, yes? Okay? That's just a formal expression of Newton's law of gravity.
The bottom would be.
Oh,
I want to say that kind of.
okay, well, just say, Mr. Collins, you're having a stupid moment, yeah?
All the lines in the second diagram should be close together.
Yeah, and I really wanted to show, to demonstrate this, I should have put more lines here, shouldn't I? To show that it's stronger.
How's the thyroid going?
Are you still on that?
Yeah, still not right.
It's different.
I'm getting used to it. It's definitely, yeah.
We work for
What is this? It's colonic irrigation. Do you know colonic irrigation? Enema. Still there's something there, and the pipe goes, you know, to the colon region of your body, and then that's colonic irrigation. You know colonic irrigation?
No.
Actually, I wrote 6.5.
Yeah, you actually, you know, in London, you go to these 7.5. It's a pressure experiment.
More than 8 hours.
You have to stop.
I know.
That's it.
I have someone set
Somebody take my folder. Guys, it's too normal. It's 140.
You've got a choice. I'm going to do something, as you said, on
Yeah.
looking at
It's
square systems.
Like that's what I want to do. She said it might be physics and not enough. What about there? Is differential equations.
Hugely complex.